Okay guys, so if we're looking at the electron, we should really just remind ourselves of what matter is made up of. I know this might sound very patronising and silly at first, but it's worth going over the basics just to be sure. So anything that has matter or mass is made of atoms, and you've been shown this kind of diagram since you were in junior cert. You've got a positive nucleus and the electrons that go around the outside, and that's broadly speaking still accurate enough. We won't be talking too much about the electron shells, that kind of stuff, but just positives, negatives, force of attraction. Okay, so I've chosen the example lithium because it's nice and small, it's easy to get your head around. So lithium's got an atomic number of 3, meaning it's got 3 protons in the center, and its mass number is 7, meaning that if you take into account those 3 protons, the rest have to be neutrons. So it's got 4 neutrons. Okay, just bodge them on there. Now in terms of electrons, however many protons you've got in a neutral atom, you're going to have the same number of electrons. So we've got our 3. The shell theory you've been taught so far says that the first 2 are going to go in the first shell, and the third one's going to go around there. Now really, it isn't as neat as all that. Neat as all that to see while going out of frame. In reality, we're talking more about probability clouds of where electrons might be at one particular time. But for now, it'll do. You've got positive nucleus, electrons going on the outside. Okay, so what's next? When we were discussing electric fields, we said that an electric field is any area of space, or if you drop a charge into it, it'll experience a force. The direction and strength of the force will depend on the strength of the electric field, its direction, and also the strength of the charge. So we usually draw it in terms of the positive charge. So if I was to drop a positive charge here, where would it go? Well, if this is a positive charge, the field lines are going to show it's going in this direction because it's repelled. So that's the convention, is that it's for a positive charge. So let's say we've got a negative electric charge dropped in here. It's going to experience a force caused by the electric field, and it's going to be attracted towards the positive charge. In doing that, it will lose potential energy as it gains kinetic energy as it starts to move, if I was to bring it in this direction. If I was to bring it against where it wants to go, if I was to push it against the direction we pulled by the positive, it would gain more energy. It would gain potential energy when it goes from this point to this point. And that measurement for the voltage is how many joules per coulombs of charge it takes. But here's where, this is why I've kind of gone a bit Play-Doh mad. That was for 1 electron. Meet the coulomb. Okay, so that's all well and good for 1 full coulomb. 1 coulomb of charge moved through 1 volt will gain or lose 1 joule of potential energy. That's grand. But a coulomb is made up of a load of electrons, 1.6 by 10 to the 19. So we're trying to find out how much energy an electron would gain or lose. It's going to be 1.6 by 10 to the minus 19 joules. Now this is such a significant number, it actually gets its own unit, and it's called the electron volt. So just to go over again, the electron volt is the amount of energy that an electron will gain or lose if it's moved through a voltage of 1. So most of the time the electrons inside a metal aren't really locked into one particular position. I can't predict that electron's going to be here or this one's going to be here. Instead they're disassociated all over the show into what we call the sea of electrons. They're always moving, they're always kind of jiggling around. Advanced simulator there. So what happens during thermionic emission? Okay, well, let's think of what the word means. Okay, so emission is just when you give something out. Therm is for thermal energy, and ionic is ions. So thermionic emission is just if we heat this up, we're going to lose ions, in this case electrons. So if you heat it up, each individual electron, which was moving around with a little bit of kinetic energy, is suddenly going to get more. So they get more kinetic energy, and eventually some of them will reach a point where they have enough kinetic energy to escape the bonds that are pulling them back into the metal. These guys here, so they'll have been emitted thermionically. Okay, one application of thermionic emission is in the cathode ray tube. Now we've already gone through it a little bit in class, but here's a couple of pointers on it again. So the heated filament heats up, warms up the cathode, causes thermionic emission, so electrons go shooting off it. They're attracted to the anode because of the high voltage between them, but some of them pass through the little gap in the center and emerges a beam of electrons. This beam can then be deflected by the 2 plates you see there, the vertical and horizontal ones, and there's also corresponding horizontal ones as well, bigger one. So a bit of a blast from the past here. Let's say you've got a magnetic field and these little dots indicate that it's coming out of the screen towards us here. And let's say you've got an electron moving into it. So let's say my electron's moving in from this side, it's going that direction. Well, we know from Fleming's left-hand rule that this moving charge in a magnetic field is going to experience a force. So we've got our field lines of the first finger coming out of the screen towards us there. Remember that the second finger for current, I'm not putting my fingers up there, not to be rude, current is the direction that a positive charge will be moving. So if this negative charge is moving in that direction, the positive would indicate in that direction. So the actual T for thrust is going to be upwards. So this direction here is going to be slowly curved. Okay, so what about when it's here? Well, the same thing again. You've got your field, current, and thrust. It's going to kind of keep being pulled inward. So the actual course it's going to take is circular. So we know that the electron is going to be forced into a circular path by the force acting on it from the magnetic field. So to find out the magnitude of that force is N, which is the number of particles, times Q, the charge on each one, times V, the velocity they're moving at, times B, the magnetic field strength. So that force is going to cause the electron to move in a circular path because it's going to act at 90 degrees to the direction of movement. So we have another name for that. That's the centripetal force, which is F. It's mv squared over r if you think back to your circular motion stuff. So sometimes you might be asked to equate the two, that the force causing this deflection is the same thing as it's the force that's moving them into a circle. So you could say that N QVB is equal to mv squared over r, and you might be asked to manipulate that formula a little bit, which we're going to try now. So we're going to continue kind of taking one step back to take two steps forward. So we're going to go back for a moment to look at charge and charging by induction. So let's imagine that this is a gold leaf electroscope. I'm not bothering with labels or detail here, it's just to get the rough idea. So as it stands, before we do anything, there's an equal amount of negative and positive charges. I'm going to stick with using blue to represent negative charges, red to represent positives, like I started with earlier, just for our own convention. So to charge by induction, let's say I move a positively charged object near the top of the electroscope. What's going to happen then is all the positive charges are going to kind of migrate away from the other positive charge, leaving with a build-up of negative charge up the top and a positive charge further away. Now if I was to remove the charged object, that would just equalize again. We're not going to give it a chance to. Instead, if you were to be touching that while you bring this close, these positive charges are going to escape kind of down your finger and away, leaving you with a negative charge on the electroscope. Now obviously we're kind of picturing what's happening here. Really it's extra electrons moving down your finger to balance it out. So in any case, you've now got a negatively charged electroscope. So imagine that before we've done that, we put a little plate of zinc on top. The process is going to be exactly the same, except this time the zinc is going to have that electric negative charge on there as well. And obviously, as I forgot, a little bit of gold leaf is going to be separated because you've got some negative charges on each side. They're going to repel each other. So that's how you can tell you've still got a negative charge going on. Okay. So we've got our negatively charged little bit of zinc on top of our electroscope. Remember, the electroscope is just there to show us what's happening. It's really the zinc that we're interested in. If I was to bring a UV lamp, now I couldn't really draw one, probably so just relabel this. So say I'm shining UV light on the zinc. Something weird starts to happen. We see that the little gold leaf starts to lose its charge, starts to come back in, because somehow the repulsive force between the negative charges here has been decreased. What's actually happening is, what's interesting is up here at the zinc, the electrons, the negative charges here have somehow escaped. They've left the premises, meaning you've got a net decrease in the charge and the gold leaf starts to kind of come back in. So the weird thing is, this will only happen with UV light. It wouldn't happen with visible light, and in fact I can easily stop it just by putting like a sheet of glass in between. So glass would let visible light through, but somehow it would block the UV light. We don't get this loss of electrons. So what's going on? Okay, so going back to our block of zinc that we were looking at earlier on, and you've got a whole lot of positive nuclei, and then the dissociated sea of electrons scattered in between them. And the strength of attraction between negative electrons and the positive nuclei is what holds zinc and all metals together. It's metallic bonding. But we were talking about what happens when you shine a UV lamp on that block of zinc. Now, it's a good point here to remember is just earlier when we were talking about charging it, about giving the zinc a negative charge, that was just so we could see with the electroscope what was happening. But this is going to happen regardless of if we go into those extra electrons. So let's just say this is a normal block of zinc. And let's say I was to shine a visible light lamp on it. Now, I could do this for ages and nothing would happen. No electrons would get lost just from visible light, because the visible light coming from this lamp here would be a mixture of all different frequencies, but there wouldn't be any UV. So we can remedy that by using our highly technical UV lamp. Now, at this point, we might want to just pause for a moment and think about light. So far, whenever you've talked about light, you've generally think about it as travelling as a wave. But light is this wave particle duality thing going on, where we say that it propagates as a wave, but that it's absorbed or emitted as a particle. That particle is the photon. So you can think of this UV lamp as a stream of photons, which I'm doing it here, each of which has a certain amount of energy attached to it. We'll get to that in a moment. As long as the energy is kind of, that's meant to be a small e, little bits of energy won't do the trick. No matter how many of them combine, it's no good. It depends on how much energy each individual photon has. So if you've got a photon from a UV lamp, it'll have a particular energy associated with it. And if that energy is enough, it can give these electrons enough energy to again escape from the positive forces that we're holding it in. To calculate how much energy one photon has, it's actually quite easy. Each photon will have an amount of energy that's equal to h, which will come to in a minute, times f. So f is the frequency of the light, and h is a new constant called Planck's constant, which is 6.6 by 10 to the minus 34 joules per second, I think. I'll verify that, but anyway. So if you want to find out how much energy each photon has, multiply its frequency by Planck's constant. And for each type of metal, it will have its own amount of energy that will be required to free these electrons from the forces holding them together. It's called the work function, and it'll be particular to an individual metal. So to find it, it's again that the symbol we use is again that phi. We multiply Planck's constant by the particular frequency that will be needed to make this happen. So the minimum frequency you need to give each photon enough energy to allow these electrons to escape. We denote it by an F with a little 0 here, and this is what's known as the threshold frequency. So any frequency below that won't be good enough. Any frequency above it will satisfy the work function and the electrons will escape. So one more time. Each photon will have an energy given by Planck's constant times the frequency of the light that emitted it. For the metal, for electrons to escape, that frequency and the energy of each photon caused by the frequency will have to be enough to make these electrons escape. That amount of energy is called the work function, and it's the Planck's constant multiplied by the minimum frequency needed to make that happen. Okay, so the UV lamp, or any lamp, will give it a stream of these photons, constant stream of photons. Now the frequency of the light doesn't affect how many photons you get, it affects the energy that each one has. So we already said that if the photons are little dinky amounts of energy, they're not going to be enough to free these electrons from their metallic prison. They have to be of a certain size. So once you get a photon that is carrying enough energy to satisfy the work function, to give each electron enough energy to escape, that's grand. What happens if you've got like the Mach Daddy of energy? Let's say that the frequency is ramped up. Each individual photon now, I've just obviously exaggerated this, has got an absolute load of energy. When that hits, what happens is the extra energy that it gives is converted into kinetic energy. So the electron not only escapes, but it escapes and goes mental, goes like loads of speed. So just to put that in a kind of equation format. So let's say that each energy, the energy of each photon is Planck's constant times the frequency of that photon. That will mean that, let's say, some of that energy will go to satisfying the work function to just get the electron to barely escape. And the rest of it, any extra, will be converted into kinetic energy, half mv squared. Sometimes we call that Ke max, because that will be the maximum speed of each electron. Some of them are going to go faster, some are going slower, but that's the maximum speed they could reach, or say the maximum kinetic energy they could reach. Okay, well, well done if you stayed with us through all of this. It's some fairly tough stuff at times. I'm going to post a second video soon enough, just cleaning up a few little bits and bobs like the photoelectric cell and some of the applications and X-rays and stuff. But for now, if you hung in with me for all that, well done. Try those questions, and I'll talk to you hopefully later on this evening or tomorrow.